All right, sorry for that. The video froze, but this time let me save it. F double prime. Are we there or are we still working? So check this novel idea. Do I ask questions to the void for fun? No. Real quickly, show me that you guys can use that muscle that runs like across your body. It's called your diaphragm. Use it and flex that muscle to change the air pressure to pull air into your lungs real quick. Show me you can do that. Okay, so everybody can breathe in. Can you breathe out? While you're breathing out, can you change the rate at which you breathe out while flexing muscles in your neck to change the shape of your vocal cords, while simultaneously changing the shape of your mouth and tongue to make ideas come out? Oh my gosh, it's just called talking. Can everybody talk? Okay, so do we need more time? Okay, so you guys probably have the following. First, derivative of the second plus the second times the derivative of the first. And I assume you kind of stopped here. Is there any obvious algebra that one could do? Like, I really have no issue if you stop here, but if, like, this isn't going to match the homework assignment, right? And we see that every time. Is there anything obvious that we could do to clean it up at least a little? Factor out what? E to the t. And then everything that's left inside, like these parentheses don't mean anything anymore. We just get t squared plus 4t plus 3. I would encourage, not require, but I would encourage, always show the work. Like if you stop here, you can, but very aware of the fact that later we're going to have to solve derivatives and stuff. So if you are not simplifying because it's a challenge, we should address it now rather than when it becomes like necessity. Okay, cool. Doable? Is it any harder to find a second or a third or a fourth derivative? Harder? No. Labor intensive? Yes. Okay. Do we need to do another second derivative or are we cool here? All right, let's get triggy. Here we go. Awkward transition. No new problems for the other one. 2.5. We are going to do trig derivatives. Or, nope, don't have a single way to word it. Trig derivatives. It's fun to rock a rhyme. To rock a rhyme that's right on time. All right. How much proof do you guys want today? Okay, that's kind of what I was expecting. When we talk about proof with derivatives, just so you guys know, it's literally just the limit. So if we were to prove something like this, if I was doing f of x plus h minus f of x, it would be, for example, sine of x plus h minus the sine of x. And then you would have to take out your trig cheat sheet and say, oh, the sine of a double angle or a sum, sine of whatever, it turns into sine x cos x. Like there's messiness that comes out of it. All of those are just limit properties and trig rules, like trig identities. We're not going to hit all those. Instead, we're just going to go ahead and give ourselves the rules. And this section is super duper short. Now, geometry, I'm crazy. Pre-calc, I'm crazy about the way that we write it. Don't write this down, but you probably remember that last year, anytime that we did stuff, I always, maybe you don't remember, but if you didn't notice, you will now. I always present them in this order, sine, cosine, tangent. It should be cosine, sine, tangent is what I should do, but I'm a creature of habit. We're going to change the order that we do them in, and there's a very particular reason. So when we write these today, I want you guys to write it down exactly like I do. Like I'm going to do 2 columns. Each are going to have 3 rows. Let's write them down all the same. So here we go. To start off with, and I'll switch. I don't want to use tildes or anything. I'm going to use asterisk. Here we go. If I wanted to take the derivative, d, and then a lot of the time we use theta, but I have no issue if we use x. Any preference? Okay. I'm going to use theta. D theta of sine theta. Okay? And I'm going to write them all here, and we're going to check in just a moment. We're going to write all 6 of them. So I'm going to use a little editing magic. Just kidding, because you need to be in the same order. I'm going to write the 3 positive or non-cofunctions together. So d theta of sine, d theta of tangent, and what's the third one that's not a cofunction? Secant. Okay, There is a reason that I'm writing all three of these together. Now, when we look at stuff, and I'm going to bounce over to Desmos, do you guys remember the graphs of sine and cosine? They're waves, right? Now, can you remember which one starts at the origin and which one starts at 0, 1? Cosine starts at the point 0, 1, and then it waves down. And we'll just check that real quick, and we'll go not to my email, we'll go here. And let's see, here's a graph of sine x. Okay, you guys were right. Sine starts at 0, and it's not set up with a trig scale, but this looks like it. So 6 point something is about 2 pi, and it's going to be exactly 2 pi. There it is. There's one period of sine right here. Okay, when I take the derivative, and I'm just going to see if I can do this. Can I do y prime? Does it understand? I'm going to try this, dy dx. It doesn't understand that either. Okay, you guys are going to get... Can you close your eyes for like 2 seconds? Okay, I have the derivative as the blue one. The red one was sine x. That's where we started, and then I said, hey, graph the derivative. It's still wavy, which is interesting, and there's even some pieces that make sense. I wish that, you know what, I can, but it's just more cumbersome. If I drew a tangent line right here, do you agree that slope would be 0? Sorry, on the red one. If I drew a tangent line right here, the slope would be 0. And notice, if the slope is 0, its derivative has a 0 right there. Okay, so I can see that just that idea of bringing them back. What's that blue graph? Cosine. It certainly is. Check it out. The reason that I wrote all three of these the same is that because they don't change sign. And what I mean by that, the derivative of sine is cosine. The derivative of tangent, and don't just look for a pattern, we only have one example, not going to like this one as much, is secant squared. Okay, and of course that means there's a natural progression happening. No, there's not. There's no pattern. That's not true. This one, d theta, if we're talking about secant, it is the secant of x times the tangent of x. Now, they're ugly, 100%. They are. However, all three of these, there's no co in front of it. They're all positive. If there's no co, it's positive. I'm going to make that note. It's up to you if you want to write it down. Not cofunction implies positive. Okay. Again, if you want to see the proofs, you can check them. They're in the text. They don't do all of them. You can probably find all of them in here, but it's just the limits. Okay. The fact that I'm making such a big deal to talk about these having not cofunctions, therefore they're positive, what do you think we're going to say happens with the cofunction parts? They're probably negative. So let's knock them out. D theta of cosine. We have d theta cotangent. And for anybody who has not seen it, theta actually looks like this. Like this is a real formal theta. It's like this. I just do it like this. That's just it looks like a planet to me. But anyway, d theta, what's the last one? Cosecant. Now, these ones, they're not as nice as some of the other rules, but it's only 3, and you'll see why I say it's only 3. Check it out. If we went here, they're all going to be negative right off the bat. Any guess on this first one? Negative sine theta. Good guess, Abigail. Okay, cotangent. This one's a little bit uglier. Negative cosecant squared. And now I don't say that there's really a true pattern that I see. This one kind of throws us for a loop. You might have been thinking it was just going to be negative secant squared, which I get it. But notice the negative did change, and we switched to the cofunction. This is a negative. I bet we just switched to the cofunction. And if I did that, we'd have negative cosecant x and cotangent x, because we just switched to the cos. That's exactly how it works. Negative cosecant x, cotangent x. Negative cosecant x, cotangent x. Okay. We have them. All 6 trig derivatives in front of us. Now, as we look at it, the rules, like there's a few times where we do just have to remember stuff, and this is one of them. I haven't gotten to this part of my musical yet, but it's coming soon. I can't stop thinking about it. Like, I'm not a playwright by any means. I want to be because I think it'd be good. Not if I did it. I'm gonna send an email to Emmanuel Miranda. Dear Mr. Miranda, I have an idea for you. All right. Cool. Example. Or we can knock out a quick pop quiz. Okay, example. Here we go. I'm just going to say differentiate. That's it. Differentiate. Cool. So for our first one, we're getting real crazy here. And this is the craziest of them all, and we're going to do them. Ooh. Love it. There's 2 that are kind of crazy. I want us to take the derivative of y equals the sine of x over the cosine of x. Okay. I'm going to give you the shortest time ever with this. Legit 15 seconds. Chat with your neighbors. Don't get an answer. I just want an approach. Like, how would you start? 15 seconds, chat with your neighbors starting right. Meow. First thoughts. Okay, in 5, 4, 3, 2, 1. I'm going to do what I heard Rafa say. I'm going to do the opposite of what Rafa said. Now, real quickly, what did you guys over there say? Because I didn't hear you. Ooh, careful. So you're trying to use quotient? Okay, could we use quotient rule? We could. And I'm going to. I'll show you. Like, I wouldn't write this down if I were you. But let's check. If we do quotient rule, it's low cosine of x d high. And what's the derivative of sine? Cos. So low d high minus high. What's the derivative of low? Instead of writing a negative sine x here, can I put the negative out front and make it a plus and write sine? Everybody catch what I did? It was sing-songy. But I just moved the negative out front. All over cosine squared. That is what the quotient rule would take me to, right? Now, just cleaning it up, let's see, we get cos squared plus sine squared, and I left off my arguments, and I'll fix that. Cosine squared x. I'm not going to use arguments in parentheses unless it's needed, because it's making it clunky for me for some reason. Cos squared x plus sine squared x all over cos squared x. Okay, it's kind of ugly. Thoughts? What's sine squared plus cos squared? 1. That is the Pythagorean identity. Now, somebody inevitably is going to try to do this. Can't do it. You could do 1 plus sine squared over cosine squared, but you can't do this. So instead, let's take that other route. This is a Pythagorean identity. It's 1 over cosine squared x. And what is 1 over cosine defined as? Not cosecant. It's secant. It's goofy. It's backward. This is secant squared of x. Now, we just got that using the quotient rule, right? This side of the room, I liked your approach more, although this one works. It works completely fine. Rafa, right off the bat, you said something else. This is just tangent. And what's the derivative of tangent? Hey, look at that. We get the same answer, but like 10 less steps. Cool. Bea's psyched about it. She's so excited. I bet she doesn't make that mistake again. Not that there's a mistake, necessarily. Okay. Be on the lookout. If you can catch this, you can save time. If you don't catch it, is it the end of the world? No. But it might be the end of your 30 seconds. All right. One more together, and then I'll have you guys knock one out. On B, I want f of x is sine x times a cosine of x. Sine of x times the cosine of x. I want you guys to differentiate and clean up to a reasonable degree. Sweet. If you're watching this on the road, go ahead and pause it and resume once you have a solution or at a point where you can't do anymore because whatever reason. And I'll see you guys in 3, 2, 1. Okay, looking at this thing. If you need it, I am always on the fence about if I would use f and g, especially with naming this f. But if we think about this as f and g, two different functions that we're taking the product of, it's first times the derivative of the second plus the second times the derivative of the first. That rule is our product rule. Now, we could expand it out if there were 3 of them. And I think that there might be a problem in your homework that asks you to do that. So before I spoil it, I want to see what you come up with. But let's kick forward. What's the first function? Sine x times, what's the derivative of the second? Negative sine x plus the second times the derivative of the first. Cosine x again. And looking at this, it looks like we have negative sine squared x plus cosine squared x. Do we all agree there? Now, I'm going to dig back through. Abigail, I do think that there's a possibility that you have a slight mistake, but yep. I'm going to write this down. Sine squared plus cos squared equals what always? Now, is this exactly that? No, so we can't really do sine squared minus cos squared. I don't think we go any further. Okay, I would stop right here. I would check that Pythagorean. The second that I have sine squareds and cos squareds, I want to think about them. But I can see that there's no way to rearrange this. I mean, there are ways to rearrange it. Should we look at one possible variation? We probably should. Could I subtract 1 and sine squared? So do you agree that if we did negative sine squared could be equal to cosine squared x minus 1? And could we, like we could, I don't know if we necessarily would, but could I replace this negative sine squared with cos squared minus 1? And maybe we could rewrite it as 2 cos squared minus, like there's variations of this that we could do. I just want everybody to be aware that they do exist. I wouldn't unless there was a particular reason that I needed to. Okay. All right. Alternatively, it is the difference of 2 squares also. Cos minus sine and cos plus sine. Maybe that'd be easier to work with. Cool. All right. One more, or just hear me out here, we could do a quiz. I take it we're starting the quiz at the start of class tomorrow. Okay, I'm fine with that. We're going to do one more example. Last example, and it's one of our good ones. We're going to work for the time, and we're just going to put it here, for 0 is less than or equal to the time t is less than or equal to 2 pi. And I don't really mind. Let's say that this is in meters and seconds. I'm cool with that. That's just a standard. So here we go. We are given for this amount of time, and there's really only a, but we're given the following. S of t is equal to 4 times the cosine of t plus 2t squared minus 1. Now, if this is our position function, and we're thinking I see a cosine, and cosine does this, I don't know the context, but if we had something hanging from a spring, and we started dropping, it would start doing this, right? Like it would rebound back and forth, it would oscillate, but it would be dampened as time goes on. That's what this would be modeling. There's something happening with bouncing up and down, whether it's the ship on like a rolling sea, doesn't matter, there's oscillations. What I want you guys to do, and I'll give you a couple minutes, is I want you guys from this to find for me the velocity when the acceleration is equal to 0 meters per second squared. So when I stop accelerating for the first time, what is my velocity? I want you guys to chat about this for a minute or 2 or 3 or 6. We'll see. Try it out. I want to see where you guys come to. I said all that without recording it. So this is your homework tonight. You guys have did I collect your homework? I did. You guys have a wonderful day. when you see runners, congratulate them. Raiders ran really well this weekend. 3rd place overall in state, which is awesome. For the boys team, 8th for the girls, which is also awesome. And don't have too much fun. Or do. I'm not your boss. What?